In this video, we will introduce the topic of set theory. Our learning objectives for this section are to define what a set is. We'll look at how to write sets in three different ways. We will define what the empty set is. We'll find the cardinality of a set and define that term. We will learn how to classify sets as finite or infinite. And we'll decide if two sets are equal or equivalent and define what those terms mean. So let's dive in. So a set is just defined as a collection of objects. A set is considered to be well-defined. Sorry, I don't have much room there. A set is well-defined if, for any given object, we can objectively decide whether it is or is not in the set. We'll look at some examples of all of these in a little bit. Each object in a set is called an element or a member of the set. One method of designing a set is called the roster method, in which elements are listed between braces, with commas between the elements. For example, here we have a set of braces, and inside we have the numbers 2, 5, and 7, right? So this is a set containing the numbers 2, 5, and 7. The order in which we list the elements is not important. It isn't important. Okay? The set 2, 5, 7 and the set 5, 2, 7, they're both the same set. They contain the same objects. The order in which you arrange them inside the braces is not important. Often, we will name sets by using a capital letter. For example, we might say that this is set S. Set S is equal to the set that contains the numbers 2, 5, and 7. Let's look at an example of where we want to write a set using the roster method. It says, write the set of months of the year that begin with the letter M. Okay, so let's start with that, then we'll answer the other questions there. So there's only 2 months that start with the letter M, the months March and May. So we can write this in set notation in the following way. We might use a letter to designate the name of the set. Maybe we'll say it's set M. We'll say M equals, we'll do an open braces, and we'll just write the elements of the set, which are March and May. And then we'll close our braces like that, okay? So we've got the braces, and then each element in the set is separated by a comma. So that is standard set notation. Is this set well-defined? Okay, this is a well-defined set because every month of the whole year either begins with M or it does not, right? There's no opinion involved. So that's what when there's if it's a well-defined set, then it's basically a set where there's no debate about what is included in the set and what's not included. So yes, this set is well-defined. Okay, let's look at some commonly used sets. The set, which we typically label with a capital N, contains the numbers 1, 2, 3, 4, etc. These are the counting numbers, or we say natural numbers. Counting numbers or natural numbers, those terms can be used interchangeably. We often use the capital letter E to represent the set of even natural numbers. So that would be 2, 4, 6, 8, etc. Set O here represents the set of odd natural numbers. So that would be the numbers 1, 3, 5, 7, etc. And notice that natural numbers are positive whole numbers, right? So that's what those are. When we are designating sets, the three dots, right, the three dots which you observe at the end of all of these sets, means that the list of elements continues indefinitely in the same pattern, right? So it's an infinitely large set. There's no way we could list all the elements, but you list a sufficient number of elements so it's clear what the pattern is, and then the three dots indicates that that pattern continues indefinitely. Let's look at another example. We want to write the set of natural numbers less than 6. We want to write the set of odd natural numbers greater than 4. And then we want to think if there's other ways we could describe these sets in words. Okay, so the set of natural numbers less than 6. Let's start with that. We're listing these in roster forms. We'll do our open brace. The natural numbers start with the number 1, and then they go up from there. So 2, 3, 4, 5. But we'll stop here because we're only interested in the natural numbers less than 6. Right? So the next number in the set of natural numbers would be 6. And 6 is not less than 6, right? So these are the only natural numbers that are less than 6. B, write the set of odd natural numbers greater than 4. Okay. Well, that would be 5. We're only interested in odd numbers, so then it would be 7, 9, 11. And this continues indefinitely, so once we have the pattern firmly established, we use the ellipses to indicate that the pattern continues. How else could we describe these sets? Okay. There's multiple ways that we could describe these sets, but just a couple of examples. The first set could be described as the set of natural numbers less than or equal to 5. Or let's write this one down. We could say it is the set of natural numbers between 0 and 6. Right? So between means greater than 0, less than 6. Okay, so that would be a way to describe it. What's another way we could describe the second set? We could maybe say, let's see, the set of odd natural numbers greater than 3. Or let's put it this way. Let's say the set of odd natural numbers greater than or equal to 5. Okay, so that would be an alternate way of describing that set. And just a couple of examples. The main point here is to illustrate that for most sets, if you're trying to describe them in words, there's more than one way to correctly describe them. Okay, let's introduce some new terminology here. This symbol right here is used to show that an object is a member or element of a set. For example, if A is the set of days of the week, we could write, use this notation, right? Monday, here's the symbol that means element. Monday is an element of set A. Monday is an element of set A. Okay. When an object is not a member of a set, we use the same symbol but with a slash through it. Okay. So that means not an element of. Let's take a look at another example here. We want to decide whether each statement is true or false. The first statement, it says, Oregon is an element of set A, where A is the set of states west of the Mississippi River. Okay. Come down here. And let's just work these out one by one. Right, so is Oregon a member or an element of the set of states west of the Mississippi? Well, Oregon is a state west of the Mississippi. So if that's how set A is defined, then yeah, it's a true statement. Oregon is a member or an element of that set, right? So this statement is true. The second one, it says 27 is an element or a member of the set that contains the numbers 1, 5, 9, 13, 17, ... right? So it looks like what we have here is that each element is 4 more than the previous element, right? So if that's the pattern, then the next element in this set would be, we'll write it down here, 17 plus 4 is 21. 21 plus 4 is 25. 25 plus 4 is 29. Okay. So it looks like 27 gets skipped when this pattern is implemented. So that means 27 is not in this set. And this is a false statement. Say false. Right, because the statement says 27 is an element of that set, and it's not an element. So that's a false statement. The last one, it says that Z is not an element of the set containing the letters V, W, X, Y, and Z. Well, if you look at the set, you can clearly see that Z is a member or an element within that set. So to say that Z is not an element of the set is also a false statement. Okay, let's move on and talk a little bit about 3 common ways to designate sets. One way is the list or roster method. And using this method, the elements are listed between braces with commas between the elements. We've seen a few examples of that already. Another method is the descriptive method, and this is just using a short verbal statement to describe the set. Okay. And then a third method, which we have not really looked at so far, is a set builder notation. And this method uses variables, and we'll explain that method a little bit later. But let's do, with this next example, let's go over using the descriptive method to describe the set B, which contains the numbers 2, 4, 6, 8, 10, and 12. And we want to describe it using words in 2 different ways. Okay. So we might describe this as, let's see, what's one way? We might describe it as even natural numbers. Even natural numbers less than 14. That's one way to describe the set. There's plenty of other ways. Another one would be to say, we might say the set of natural numbers that are between 1 and 15 that are divisible by 2. Okay, so those are two valid ways of describing the set in words. I'm sure you could come up with some other ways as well. The third method of designating a set is using set builder notation. And this method uses variables. A variable is a symbol, and we usually use a letter to represent it, that can represent different elements of a set. So set builder notation uses a variable, braces, and a vertical bar, and the vertical bar is interpreted using the words such that. For example, the set in roster form containing the numbers 1, 2, 3, 4, 5, and 6 can be written in set builder notation to look like this. And the way we would represent this, we would say this is the set of all elements x, then the vertical bar means such that x, here's our symbol that means a member of or an element of, so it means x is an element of n, and n represents the set of natural numbers, right? X is a member of the set of natural numbers, and x is less than 7, right? So we could read this as the set of elements x, such that x is a natural number and x is less than 7. Okay. Let's do another example using set builder notation. So we want to use set builder notation to designate each set, and then think about how your answer could be read aloud. So the first one, the set R contains the elements 2, 4, and 6. The set W contains the elements red, yellow, and blue. So let's think about two ways we could, or the ways we could write these two sets using set builder notation. Start with A. Let's call this, so this is set R. We'll do an open braces. We'll put an X and then a vertical line, another X, or a member of symbol, a capital E, and we'll say X is less than 7. Okay. So how might we write this in words? We could say the set of all x such that x is an even natural number and x is less than 7. Okay, that would be an accurate way of describing that in words. All right, how about the next one? The next one, this is B. We have W. And if we're very observant, we'll notice that the three colors listed are all primary colors. So we could say that W equals all x, vertical line, and then x is a primary color. Close brace. Okay, so we could describe this in words. The set of all x such that x is a primary color. And there you go. All right, our next example, we have the set S that contains the elements 32, 33, 34, 35, ... And we want to denote this set using the roster method, the descriptive method, and set builder notation. All three methods. Okay. For A, in roster form, in the roster method, we could just do a set of braces and just list the numbers, right? 32, 33, 34, 35, and we have to include the ellipses to indicate that this continues indefinitely. For B, we just want to use words to describe what the set is. Again, there's probably more than one right answer here, but we'll call it this. We'll say the set S is the set of natural numbers greater than 31. Okay. Using set builder notation, we might do something like this. We'll say X and then the vertical line, which means such that X is a member of the set of natural numbers and X is greater than 31. Okay? All right. Moving on. If a set contains many elements, we can again use an ellipsis to represent the missing elements as long as we illustrate a clear pattern. For example, the set of natural numbers from 1 to 100, right? If you listed them all out, that would be a lot of numbers. 1, 2, 3, 4, 5, all the way up to 100. So it's a finite set, but it has a lot of elements, right? So what we do is we list the first few elements of the set. Then we put the ellipses, and then we list the last few elements of the set, right? So you just got to make sure to include enough elements at the beginning and the end so it's pretty clear what the pattern is. So in this example, let's use the roster method to write the set containing all even natural numbers between 99 and 201. Okay, so the solution here, the first element of the set, right, that's a pretty bad brace. Let me see if I can do a better job with that. Would be the number 100. And then because we're just interested in even, the next one would be 102, and then 104. And then what we'll do is we'll put our ellipsis, 3 dots, and then we'll say maybe the last two elements of the set, 198 and 200, okay? And that would be a perfectly fine way of expressing the set in roster form in this case, for this large set. Okay. Okay, a set with no elements is called an empty set. It's also called a null set. Okay, still considered a set. It's just a set that has nothing in it. The symbols used to represent the empty set, there's two ways to do it. Either just a set of braces with nothing between them, or a circle with a slash through it. Okay, those both mean the exact same thing. They mean the empty set, right? The set that has nothing in it. So let's look at this example. We want to say which of the following sets are empty. Okay. Starting with A, the set of woolly mammoth fossils in museums. Okay. Well, there is certainly at least one woolly mammoth fossil in a museum somewhere, right? I've seen some. So this set is definitely not empty, right? It has elements in it. Not empty. B. All the set, the second one for part B, it's in set builder notation, and we would read that as all X such that X is a living woolly mammoth. As far as I know, there are no living woolly mammoths. Woolly mammoths have been extinct for almost 8,000 years, so this is most definitely an empty set. There are no elements in that set. Okay, C. That one's a little tricky because we said earlier that there's two ways to represent the empty set. One is using an empty set of braces. Another is this circle with a slash through it. Now here it kind of seems like we're combining both of those ideas, right? But this is not an accurate way to depict an empty set, okay? This is actually a set with a single element in it, and the element is this symbol right here, right? That's the symbol that represents the empty set, but putting it inside a set of braces is not an accurate way of depicting the empty set, okay? So that's not empty. Okay. Okay, the last one, D. All X such that X is a natural number between 1 and 2. Well, natural numbers are only whole numbers. They cannot be fractions or decimals, and the only numbers that fall between 1 and 2 are decimals or fractions, right? So there are not any natural numbers between 1 and 2. So that is an empty set. Okay, let's define a new term, and that is the cardinal number of a set. The cardinal number, let's say, write that in here, cardinal of a set is the number of elements in a set. That's all it is. Okay, so for a set A, the symbol for the cardinality is a lowercase n parentheses a, which is read as n of a. But what it represents is just the number of elements in the set. So to illustrate this with an example, we also, sometimes instead of saying cardinal number, we'll say cardinality, but they really mean the same thing, okay? Just the number of elements in a set. So example 9, find the cardinality or the cardinal number of each set. Okay. For A, we'll say n of A. We just count the number of elements in the set, right? 1, 2, 3, 4, 5, 6. So the cardinal number of that set is 6. B, this one's in set builder notation, but it says all X such that X is a natural number and X is less than 16, right? So we're talking about the natural or the counting numbers that are less than 16. So that would be starting with 1, and then 2, and then 3, and then 4, and going all the way up to 15, right? Those are the natural numbers that are less than 16, and there are 15 of them. So that's the cardinal number. N of B equals 15. See? Well, this is a set that only has a single element, right? It has the element of 16. That's it. So the cardinal number there is just 1. Okay. And then for D, we see the circle with the slash through it. that represents the empty set. And the empty set is the set that has no elements in it, right? So we might say the cardinal number of the empty set is equal to 0, because there are no elements in an empty set. Okay, let's define a couple of other terms. A set is called finite. Finite. Sorry, if it has either no elements or if it has a cardinality that is a natural number. Okay. A set that is not finite is called an infinite set. Okay, so a finite set has a finite number of elements. An infinite set has an infinite number of elements. Okay, so we've looked at a few infinite sets where we use the ellipses kind of at the end to indicate that it continues forever, right? So let's look at an example where we want to classify a few sets as either finite or infinite. The first one is in set builder notation. It says all x, this is for part A, all x such that x is a natural number and x is less than 100. Okay. This set is finite. Sorry, can't write today. It's finite because there are 99 natural numbers that are less than 100, right? So the cardinal number of this set is 99. It has a finite number of elements. Okay, for part B. Set R is the set of letters used to make Roman numerals. This set is finite too, right? Because the letters used to make Roman numerals, well, those are the letters C, D, I, L, M, V, and X. There are not any additional letters, right? So that's the list of elements in that set, and it's a finite number, right? So that set is finite. For part C, we have the set that starts with 100, then it goes to 102, 104, 106, but the ... the ellipsis there indicates that it continues forever. So this one is infinite. Since it consists of an unlimited number of elements. Okay. D. Set M is the set of people who went to your elementary school. Well, this set is finite as well, because the number of people who have gone to a specific elementary school is a finite number of people. Now, depending on how old the school is, it's probably a very large number of people, but it's still a fixed or a finite number. Okay. E. Set S is the set of songs that can be written. Well, we would call this one infinite, right? Because technically, there's no limit on the number of songs that could be written, right? You could write anything, almost any phrase down, and call it a song title or make a song about it if you want to, right? So no limits there. So it's an infinite set. Okay, moving on, let's define a couple of other terms here. Two sets A and B are equal, written A equals B, if they have exactly the same members or elements. Two finite sets A and B are said to be equivalent and the symbol for equivalent is an equal sign with that little squiggly mark over the top, if they have the same number of elements. So they have the same cardinality. N of A is equal to N of B. Okay. For example, the two sets A, B, C and C, B, A, they are equal because they have exactly the same members, an A, a B, and a C. Remember, the order doesn't really matter. The set of all names of students in your class and the set of their student ID numbers, these are equivalent sets, right? Because they have the same number of elements, but they have different elements. So the sets are not equal. Okay, for this next example, we want to state whether each pair of sets is equal, equivalent, or neither. So the first one, we have the set PQRS as the first set, and the set ABCD as the second set. Well, clearly they contain different elements, so they are not equal, but they do both contain exactly 4 elements, right? So they have the same cardinal number, so they are equivalent. Sorry, that should be an A in there. B. For B, we have the first set has the numbers 8, 10, 12, and the second set has the numbers 12, 8, 10. Well, they have exactly the same elements, and they have the same number of elements. So they are both equal and equivalent. In fact, equal sets will always also be equivalent, right? But equivalent sets will not necessarily be equal. C, well, the first set contains the number 213, and the second set contains the individual digits 2, 1, and 3. So the first set contains 1 element, the other one contains 3 elements, so they are not equivalent, and they also contain different elements, right? So they are not equal either. So we would say neither. D. The first set there has the numbers 1, 2, 10, and 20. That's 4 elements. The second set has the numbers 2, 1, 20, and 11, also 4 elements, so they are equivalent. And it looks like they share several elements in common, but not all of them, right? They both have a 1 and a 2 and a 10, but then one set has a 20, the other one has an 11, right? So the elements in the sets, while they are almost the same, all the same, they're not exactly the same. So they are not equal. So we would say they are equivalent, but they are not equal. E, we have a set in description form, even natural numbers less than 10, right? So that would be the numbers 2, 4, 6, and 8. And the second set in roster form lists exactly those numbers, right? The numbers 2, 4, 6, and 8. So those are equal sets, and they're also equivalent. Okay. All right, and yeah, so that wraps up this topic, just introducing some of the basic concepts of set theory, and we'll continue diving into this topic a bit more in the future Chapter 2 videos. So we will stop here for today.